Okay, good evening, everyone, and well, good morning to our US friends, and good afternoon to Europeans. So it's a great pleasure to introduce Riddhi, who is today's speaker. So Riddhi did his master's in IIT Kanpur, so he's our alumnus, and then he went to do a PhD in Delaware with Bill Matthews. And after that, he's at Princeton as a postdoc working on solar. He, in fact, is a research scientist, not more than a postdoc. Uh, and he's working on solar wind, uh, Parker probe results, and so on. So today he's going to talk about some of this stuff. So Riddhi, please take
Thank
over.
you. Let me share. Here we go. Okay. Do you see its full screen?
Yes.
Okay. Thank you for the introduction, and thank you for letting me speak here. It's a great opportunity. Here we go. Okay, so as the title suggests, I'm going to talk about this historical event, Parker Solar Probe entering the solar corona. There has been some recent updates, so I thought this would be a great platform to share the news with folks. And I'm going to present not only my works, but some other works by some other folks too. And yeah, feel free to stop me if you have any difficulty understanding. So these are my collaborators. This work has been done with. So outline, I'm going to talk about, if you don't know what is the Parker Solar Probe mission, I'm going to talk about the mission first. Then I'm going to talk about this Alfvén critical surface, or rather the Alfvén zone, and PSP or Parker Solar Probe crossing this surface or zone during its recent orbits. And then I'm going to characterize the Sub-Alfvénic solar wind, the solar wind beyond this point. And we're going to talk about specifically turbulence, anisotropy, intermittency, and magnetic field switchbacks. And then we are going to end with a discussion and a summary. So first, Parker Solar Probe, let's talk about the mission if you don't know about it. So it's, I think, fifth or sixth mission in NASA's Living with a Star program. Basically, the goal and objective of the mission is that we live with a star, the sun. So it's a good idea to understand something about the star and what effects it has on Earth's atmosphere. Here is Parker being launched in 2018, August, from Cape Canaveral in Florida. Here is the spacecraft ready to be shipped to the spacecraft launch vehicle. And here is the artist impression of how the spacecraft looks when it is near the sun. So the novelty of this mission was that it was being sent very close to the sun. So we have had many missions which orbit near the Earth, right? So we send the spacecraft outside the Earth's gravity sort of, but it orbits in Lagrangian 1 point or so on. We have had spacecraft go to the moon. You may know about the Voyager mission, which recently went outside the solar system into the interstellar media. But we have never had a mission going very close to the sun, in sun's atmosphere. So that's what Parker was designed to explore the region. And the difficulty, of course, as you can imagine, is it gets very hot near the sun. So they had to wait for the technology to withstand those temperatures and so on. So here is the shield, the famous Parker Solar Probe shield. This is made with some material which can withstand about 1000 degrees Celsius on one side of it, but keeps the other side, the side behind it, at almost room temperature, about 80 Fahrenheit or so on. So the instruments which are behind this shield can operate okay without being burnt or so on. And it is named after Eugene Parker, who discovered solar wind. Here you can see Eugene Parker watching the launch actually. So this actual site, he's watching it being launched from Cape Canaveral. I should mention this is the first mission of NASA to be named after a living scientist. All other past missions which have been named after a scientist, all the scientists had passed. And like I said, the novelty of the mission is that it goes very close to the sun, right? So here's a trajectory or the planned orbit of the mission. So it was launched from Earth's orbit around here. From then on, even in the first orbit, you can see it went closer than Mercury's orbit. And then progressively in the future orbit, it gets closer and closer to the sun. The yellow are the past orbit and the red denotes the future orbits. So in the final orbit, it is supposed to go closer to 10 solar radii. It will go closer to 10 solar radii to the sun. Okay, now why send a spacecraft very close to the sun, and specifically what is the solar corona? So if you ask a solar physicist, they'll say that the solar corona is the outer atmosphere of the sun. So the whole solar wind can be considered as the outer atmosphere of the sun, right? So which region are we really interested in? So let's think about this diagram for a moment. This is just a 1D diagram. So if you think about the solar wind speed near the Earth, it has a value of about 700, 600 kilometers per second, right? And if you go closer in, close to the sun, for remote sensing data and modeling suggests that the solar wind is accelerated in this region from around 1, 2, 3, 4, 5 solar radii, right? So this is the region where the solar wind speed is ramped up and then it kind of saturates to a stable value. So this right here is the solar wind acceleration region, right? So this is the region we're interested in. You may also be aware of the coronal heating problem, where again, within a few solar radii of the sun, about within 5 solar radii, if you go away from the sun, the temperature increases instead of decreasing, right? So that's the anomalous coronal heating problem. That also requires you to go very close to the sun in this region, which was never explored before. This is also the region where solar energetic particles are accelerated. By the time they receive near the, by the time they reach near the Earth, they already have been processed via diffusion and other processes, right? So you cannot distinguish acceleration with transport. So you need to send a spacecraft very close to the sun to disentangle the transport with the acceleration mechanism. So that's why this region is very interesting. And specifically this point, which I'm going to talk about in a minute, where the Alfvén speed and the solar wind speed becomes equal. So the Alfvén speed is the speed of Alfvén wave, which is given by a formula like this in CGS unit, right? So Alfvén waves are a wave in incompressible MHD. They transform information and so on. But the formula for Alfvén velocity is given by something like this. It's the magnetic field divided by the square root of the mass density. So close to the sun, the magnetic field is very strong. So the Alfvén speed is very high. But then away from the sun, the magnetic field becomes weaker and weaker. So the Alfvén speed drops. And the solar wind speed, like I said, increases close to the sun and then becomes saturated. So there comes a point where these two become equal, right? And then within this region, the Alfvén speed is greater than the solar wind speed. So physically, you can think that this region is magnetically dominated, right? Rather than kinetic energy dominated, because the energy in the magnetic field dominates over the energy in the kinetic field. But in this region, U dominates over V Alfvén. So this region is kinetic energy dominated. So the kinetic energy dominates over the magnetic field energy. So that's why this transition region and the region inside this point is of interest. And that's what we actually mean by lower corona. And that was the goal. This region is the goal to be explored by Parker Solar Probe. It was estimated that this would happen near about 11 or 12 solar radii, but those are just model empiric numbers. And this I'm quoting from the mission's official objectives. It's to determine the structure and dynamics of sun's coronal magnetic field, to understand how the corona is heated and what accelerates the solar wind, and to understand solar energetic particle acceleration. So these are the goals and objective. And the point where this transition happens where the solar wind speed takes over the Alfvén speed is called the Alfvén radius, this point. So let's talk about that. So we so far discussed 1D problem. That's why it was the Alfvén radius. In a 3D, you can imagine it can be generalized to Alfvén critical surface, right? So
Riddhi, can you go back to the previous slide?
Sure.
So these are mean velocity field and mean Alfvén speeds. Now there will be
Right.
RMS as well, no fluctuations.
No, these are not fluctuation. I'm talking about the mean, the bulk.
I know. So
Okay.
how do the fluctuation scale? Because sometimes the fluctuations matter, no, not
right.
the mean.
Yeah, very
So
good question.
can you comment on it? I don't know about this, but
sure. I would also say in this region, because it is magnetically dominant, so the fluctuations are very constrained. They don't have much room so as to evolve. But outside the region, once it becomes kinetic energy dominated, the fluctuations start becoming more important. So this region is more nonlinear and turbulence dominated, whereas this region is very constrained and the fluctuations don't have much effect. Exactly.
So the left region, weak turbulence could be a good approximation.
Yes, right. Reduced MHD is actually a very good model that is often invoked to describe this region.
I see. Okay, great. Please continue.
Thank you. Yeah, it actually clarifies some issues. So Alfvén surface, we were talking about it. So yeah, recall that the Alfvén surface, Alfvén radius is the distance where the solar wind takes over the Alfvén speed. So using a very naive model of an untilted dipole modeling the sun solar wind, you can imagine the Alfvén surface like this white curve, right? It has a shape like this. Close to the sun, the magnetic field looks like this, radially outward. Here, in the solar max condition, where there is more variability in sun's magnetic field, the Alfvén surface may look like even more distorted, right, than this left figure. So this pink contour represents the Alfvén critical surface. So we're interested in the solar wind inside this surface. Okay, that's a simple picture, but actually, if you think a little bit
go back.
Yes.
Go back. So if Parker is lucky, it could go in quite close. No, I mean, right. So what is the radius where the pink line is? There's the inner circle. So depends. If Parker is lucky, it could get inside the Alfvénic zone, or it could be just outside the Alfvénic zone. Depends on.
Yes. If it and like I'm going to present, it has actually gone inside the Alfvén surface, luckily. But yeah, if we had been very unlucky, it could have always went outside the Alfvén surface. I agree.
I see. Okay.
Yeah, but that's the whole preface. But yeah, those are done with actually very simple calculation, not including fluctuations, including only mean variables. If you include the fluctuation, you can actually imagine it's not a surface, rather a zone, right? So on top of this envelope that I was showing in the last slide, if you put in the turbulence fluctuation, the quantities might actually look like this. So for example, here we're plotting the Alfvén Mach number, which is the ratio of the solar wind speed to the Alfvén speed. And the red colors denote high values, and the blue colors denote low values. And actually, and this has been done using a transport-based solar wind simulation.
Riddhi?
Yes.
But here for the Mach number, are we talking about RMS Mach number or always average Mach number? I mean, the
no.
Yeah.
This is not the turbulent Mach number. This is the
normal Mach number. I mean, VSW bar. Okay.
Yes, bulk velocity over the bulk Alfvén velocity.
Okay.
The right figure is the same as this, but instead of color coding all the values, we color code depending on whether the Mach number is below 1 or above 1. So where solar wind speed is less than Alfvén speed, the points are yellow, and if it is more than, it's blue, or whatever you want to say, teal, cyan. So you can imagine it's not a surface anymore, right? But rather it's a zone. Very close to the sun, you'll always have Mach number less than 1. And very far out, you'll always have Mach number greater than 1. And somewhere in between, you'll sometimes have less than 1, sometimes have more than 1. So that's the concept we should think about. It's the Alfvén zone, not a surface. And here are just two comparisons. We flew virtual spacecraft through this simulation using the Parker trajectory. And you can see the model and the data reproduce quite close. And here they're going below 1. Okay, so we have clarified this picture. Now talk about Parker crossing this Alfvén zone or surface, however you want to imagine. So during its 8th orbit near the perihelion, so perihelion is when the spacecraft goes closest to the sun. So this is where it happens. I hope you can see the green arrow right in this region. And in these 3 gray boxes, the Alfvén Mach number, where it is shown in this panel, ratio of the bulk velocity to the Alfvén velocity goes below 1 for extended periods of time. I show the magnetic field components here, density, electron density here. Here's the radial speed and the Alfvén speed, and here's the plasma beta. This was reported in a paper by Kaspar et al. In Physical Review Letter. And I've mentioned these paper, Gosling et al. In 1982 and some more, just to note that this is not actually the first time we have seen Alfvén Mach number below 1. Even close at 1 AU, 1 astronomical unit near the Earth, even though it is very rare, we have seen bursts of wind where the Alfvén Mach number goes below 1. This was the first report, Gosling et al. In 1982. But the difference is all the previous observations, the periods with sub-Alfvénic solar wind have been very small, less than a correlation length in turbulence. But here, these periods are extended periods of sub-Alfvénic solar wind, many times the correlation length or time of the turbulence fluctuation. So if you compute the correlation length or time, these periods are actually many times more than that. So these suggest that the Alfvén Mach number going below 1 is not due to just some turbulence coincident. It is actually going below the Alfvén surface or region. So that's the novelty of these observations.
So just wondering, one more question. Has the energy spectrum and has been or structure function been computed for this region? I'm sure.
Yes.
So what do they show?
In the Kaspar et al. Paper, they kind of did it for the whole thing, everything combined, the super-Alfvénic and sub-Alfvénic. I'm going to show one plot by Zank, who did it separately for the sub-Alfvénic and super-Alfvénic.
Okay.
There are some challenges to computing that. You can only compute the frequency spectrum. Yeah, and I'm going to talk about this. You can no longer invoke the Taylor hypothesis to interpret it as a wave number spectrum. So how much of use it is a matter of discussion, but I'm going to come to that.
Okay.
So yeah, these observations were done during its period. It was kind of a big deal. We had several press release and news media output about this. Here I'm showing a cartoon by PhD Comics. If you don't know about PhD Comics, go follow it. It's a wonderful, sort of thing in the dark hours during grad school or whatever. They give some funny comics. But yeah, here they're comparing to Greek mythology of going close to the sun. It also featured in Saturday Night Live, which if some of you had, if you follow the US sort of media in the East Coast, it's a comedy sketch. And here you can see Tina Fey making this joke about, you don't see the joke here, but the joke was that NASA sent a spacecraft to the sun, and they were able to do it by launching the spacecraft at night when the sun was not there. So anyway, it made some news media. So we thought that why don't we characterize this sub-Alfvénic solar wind? And so what we did here, I already showed you the picture from the 8th perihelion. We also took the data from the 9th perihelion, so from the next orbit. In the next orbit also, close to the sun, here, we saw another extended interval where the solar wind Mach number shown in the top panel goes below 1 for an extended period of time. So what we did, we compared the super-Alfvénic and the sub-Alfvénic interval in the neighboring points. So even though these intervals, say for example, this super-Alfvénic interval and this sub-Alfvénic interval, even though they are almost at the same solar radii from the sun, they are not very different in terms of distance. Do they differ in the turbulence properties, right? Like MKV was saying, spectra and so on, or are they of similar characteristic? We wanted to address that. There are some limitations I want to discuss first. So first, in the proton velocity, only the radial component was accurate or accessible. Due to some instrumental limitations, the other two components were not so reliable. So we could not use that. You could only use the radial speed. Electron density. So proton density again was not of enough accuracy to be used. So we had to use only the electron density. Assuming quasi-neutrality, you can assume that the electron and proton density are the same. So that's fine. But just making you aware of these limitations. And now coming to this point, Taylor hypothesis. So those of who do space physics, you may know that something we often use to do turbulence using spacecraft data is invoke Taylor hypothesis, right? Where if your solar wind speed is much higher than the Alfvén speed, which is true most of the time close to the Earth, then you can interpret this time series as a spatial cut through the plasma. You can assume that the plasma is essentially frozen in. So during this time, it does not evolve that much nonlinearly. And you can interpret it as a 1D cut to the plasma. And you can do your wave number spectra or structure function on everything that you usually do. But here, explicitly, you cannot do that, right? At least not in a straightforward way, because the condition is very, not only poorly valid, it's actually invalid. Your solar
Riddhi, I will not agree with you.
Okay.
I'm sorry to.
Want to discuss
It
now?
depends on fluctuations. Fluctuations. Solar wind
I,
VCSW will not be turbulent. What about the fluctuations?
no, so both are required. Thanks for bringing that up. For Taylor hypothesis to be valid, one condition is what MKV is saying, your delta V over V solar wind has to be much less than 1, yes. So your solar wind fluctuations should be less than the mean speed, but also your bulk speed should be higher than the Alfvén speed, because otherwise Alfvén speed is the speed in which your nonlinear sort of large eddies evolve, right? If you do a time scale in both, one is L over delta V, but the other is L over VA.
I think
Both
this
time
is
scales
mixing up too many things, which is.
So, Bharmaji, just to complement your comment, actually, so I mean, there are papers where they explicitly calculated the Taylor hypothesis things. One is by Fuatsa-Arui, and I also did some calculation explicitly in my thesis. So I will show you. I mean, exactly the mean solar field, mean solar velocity actually comes into play there. Yeah.
I see.
I would think so. Yeah.
So anyway, let's discuss it later. But I want that clarification in the end.
I think both are important.
Okay.
But at least, yeah, it's not straightforward if you can use the Taylor hypothesis or not. And people are working on some modified versions of it, if you can use some other formula, but at least you cannot do it in the usual way. So yeah, we have to keep these limitations in mind, before doing the problem. So we had to come up with problems which could be done without using the Taylor hypothesis, and that could be done with just the radial speed and the electron density and so on. So keeping that in mind, let's move on. So first we start with turbulence, just the plain turbulence amplitude. I think everyone knows about it, so I'm not giving any background. We take just the magnetic field data. Again, we do not use the Elsasser or velocity data because like I said, all components of velocity may not be reliable, but the magnetic field was fine, all three components. So we take the magnetic field data and you calculate the turbulence amplitude. Here is the formula. You basically subtract out the mean and then you take the RMS fluctuation. And then you accumulate all your data from the subalfvénic intervals and all your data from the superalfvénic intervals together, and we just drew two histograms of the log of the turbulence amplitude for these two separate populations. We used about 10-minute intervals to do this averaging. And when you do that, you see there's clear distinction between the two populations. The superalfvénic intervals, remember, even though they are roughly in the same radial distance as the subalfvénic intervals, the turbulence amplitude is shifted systematically from the subalfvénic intervals. It can be quantitatively seen from this table. So the mode or the most probable value of the delta B in the superalfvénic interval is considerably higher. I forgot to put in the units, but these are in nanotesla. When you take the log, the unit goes away. But before taking the log, it's in the usual nanotesla unit. But the point is the superalfvénic interval, the most probable value is considerably higher than the subalfvénic interval, right? And you can see this from the figure as well. The peak in the histograms are shifted. If you calculate the average, same thing. Your superalfvénic interval has a higher average than the subalfvénic intervals. And here are the standard deviation. So the conclusion is that turbulence is reduced in the subalfvénic wind, right? The subalfvénic population has systematically less turbulence amplitude than the superalfvénic interval, even though they are roughly in the same radial distance. And
let me get super
yes.
is inside the 10 AU. Super is when
No.
V alpha is bigger, right?
No, precisely the opposite.
So super U is bigger. Super U is bigger.
Yes, okay. Superalfvénic is when Mach number is greater than 1. So when solar wind speed is greater than the Alfvén speed. And subalfvénic is the new one.
It's outside. So turbulence is stronger outside.
Yes,
region.
Exactly. Turbulence is stronger outside the Alfvén surface. Which is what you may expect, right?
Yeah, that's weak turbulence or strong turbulence is some signature of that.
Exactly. Just like the points you were raising, the fluctuations have more sort of degrees of freedom outside the Alfvén surface. They have room to evolve and so on. Nonlinear processes dominate. That's why turbulence seems to be increased right out at the surface. The Alabama group, Gary Zhang's group, they were also working on, I think, similar problem at the same time, and they had a paper come out just few weeks after ours. And they calculated the spectrum. Here, the Z plus Z minus spectrum. And again, notice that it's only frequency spectrum. They do not, at least here, they do not show the wave number spectrum. So it's not straightforward.
Okay, just one second. So F minus 1.5. So these two curves are Z plus Z minus, and one is 1.25.
Z minus is 1.25 and Z plus is 1.5. And the left panel is for subalfvén period and the right panel is for superalfvén. And they are showing here that both are showing similar behavior in terms of spectra. No difference.
I see.
But if you notice the level of fluctuation, you can clearly see that the superalfvén interval has more turbulence.
I see.
So I think it's consistent with their picture, but we do not do any spectra because of the limitations I said. Because it's a Fourier spectra, it's not exactly straightforward how you interpret that. So that's what we saw in turbulence. Let's move on to anisotropy now. So this I'll give a little bit background because not everyone may know about solar wind anisotropy. So unlike hydro or unlike hydrodynamic turbulence, in MHD or even in plasma turbulence, since you have a mean magnetic field which cannot be transformed away by a Galilean transformation, it breaks the isotropy and makes the system anisotropic if you have a mean magnetic field. Shevlin et al. And Norton et al. Started this, and there have been many more papers since then. In the solar wind, right? If you think about the sun here, the sun has a mean magnetic field, which you may know is known as the Parker spiral. So say the Parker spiral and the mean magnetic field is like this. If your spacecraft is sitting here like this, then you'll have a broken anisotropy, right? In this direction. It's a figure from Brunner and Carbone. So in the solar wind, this Parker spiral does break the anisotropy, and you do see anisotropy in the solar wind fluctuations. Now, anisotropy can be defined in many different ways. You have wave vector or spectral anisotropy, where the power in your K parallel may not be same as your power in K perpendicular. You will have variance anisotropy, which does not look at the wave number at all, but just the fluctuation amplitude in the parallel and the perpendicular direction, and they are not equal, and many more. So now remember, I talked about the limitations. You cannot use Taylor hypothesis. So it's not straightforward how you'll get wave number from frequency. So I think right now we can only do variance anisotropy with these observations in a straightforward way. So you just calculate the amplitude in a parallel and perpendicular direction and see if they're similar or not. So that's what we did. So we wanted to investigate variance anisotropy in the sub and super-Alfvénic periods.
But here the perpendicular and the parallel means like with respect to the global mean field or local mean field?
Yeah. So you choose your averaging interval, right? Okay. And then you transform your coordinate to the mean field coordinate. But
so yeah, it's a global mean field actually.
It's a global mean field.
Okay.
Precisely, yeah. What we call it global mean field. Yeah.
Yeah. Sure.
So again, just to remind you, the definition is like this: variance anisotropy A sub B is given like this. So in the mean field coordinate system is the fluctuation in the perpendicular plane over the fluctuation in the parallel plane, and these are the averaging interval Supratik was talking about. So it's a global mean field, you can say. And for isotropic distribution, this should have a value of 2, right? In solar wind, we usually observe value higher than 2, so it's anisotropic. We use 10 minutes averaging interval again. And
I would put 2 in the bottom. So we do it often.
Oh, right, to make
AB
it 1.
becomes 1.
Yes. True.
So that's a convenient thing to put if you guys.
Now I recall, yeah, your paper, and I think people in MHD community do that. I don't know why people in space physics don't do that. True, I agree. If you put in a 2 in the bottom, it becomes 1. Anyway, we do the same thing like we did in turbulence amplitude. You gather all your points in the Sub-Alfvénic regions in one population, and you gather all your points in super-Alfvénic population in another bin, and then you do a histogram of the variance anisotropy. And again, you see both populations are anisotropic, but the Sub-Alfvénic region, the orange which we are interested in, is systematically more anisotropic than the super-Alfvénic region, right? Again, going a little bit quantitative, the most probable value in the Sub-Alfvénic region is now higher than the super-Alfvénic region. The mean is also higher in the Sub-Alfvénic region than the super-Alfvénic population. So we conclude that anisotropy is enhanced in the Sub-Alfvénic. So inside this surface, anisotropy is enhanced compared to outside the surface, which again makes sense, right? Inside the surface, like I said, the magnetic field dominates, so you have more anisotropy, whereas outside the surface, you start to have fluctuations. Fluctuations are starting to take over, so anisotropy is starting to get reduced gradually. So that makes sense, I think. Having talked about turbulence and anisotropy, we do intermittency. Again, I'm going to give you a little bit introduction if folks are not aware of what intermittency is. So here, in any turbulent system, specifically in plasma or the MHD, if you plot the current density, you will see that it's distributed like this. In fluid, if you plot the vorticity, you'll have similar distribution. The current density are very high enhanced in these current sheets, as we say. In hydro, you'll have vortex sheets. So this is what we mean by intermittent distribution. So if you make a PDF of the current from this turbulence simulation, let's say, it will have a distribution like this. And if you compare it with a Gaussian, this distribution is super Gaussian. So these regions have a fat tail, which goes beyond the Gaussian distribution. And you can interpret what the core and the side and the fat tails are associated with. These tails, these Sub-Alfvénic distributions, associated with these current sheets. So in the boundaries of these magnetic islands, you have these high current values, and that's what this super Gaussian population is represented by. In space physics, at least in situ data, a convenient way to quantify intermittency is via PVI, or partial variance of increment, which is defined like this. But rather than the mathematical definition, I think the physical meaning is that high PVI values denote intermittent structures. So all these points where you see these PVI values, this is from simulation and this is from Sub-Alfvénic data. And both you see often have these high values, and these high spikes of PVI are associated with this current sheets region. So wherever you have a high current density, you'll have a high PVI. And I'll come back to this point later. But that's what PVI denotes. Why do we care about intermittency in space physics? Intermittency is related to particle energization. It has been shown that energetic particle flux increase with PVI values. So again, current sheets or wherever the PVI values are high, you'll have higher flux of energetic particle. And this is a straightforward correlation analysis. This is a superposed epoch analysis. So at high PVI events, so say PVI greater than 6, your energetic particle flux is higher. And then as you move away from the point, your energetic particle flux decreases. Not only energetic particle, your temperature of the population also increases at PVI. So say the red lab point, which denotes PVI greater than 5, again, you see at 0 separation at high PVI event, your temperature is highest. And then as you move on from the current sheet or the PVI region, your temperature decreases. So high PVI regions are associated with higher temperature and higher energetic particle flux. So we wanted to study intermittency in this super and Sub-Alfvénic population. And again, I'd like to remind you, this is a definition, and here is a figure showing PVI square and current density square. And you can see that the PVI follows current density quite well, right? And that's why actually PVI was designed, because in using instrument data, oftentimes you cannot calculate electric current. Like for example, even Parker doesn't have good enough measurement of ion and electron velocity both to measure current. So you use PVI sort of to get the current sheets and the coherent events. And again, because it's a time thing, you do not have to convert it to space to do this PVI. So even without invoking Taylor hypothesis, you can do this calculation. So just like the previous two analysis, here also we accumulated the Sub-Alfvénic and the Super-Alfvénic population in 2 different bins, and we drew the histogram. I should have mentioned before, PVI values greater than 2 denotes coherent structure or intermittent structure, current sheets, right? So the fat tails in the Gaussian I was showing, those are all associated with high PVI, but how much high? Higher than at least 2.5. No one cares about PVI less than 2.5, that's to say. Only PVI higher than 2.5, those are the points we're interested in. We choose a 10-minute averaging interval as before, and we choose a lag of about 1 second. And then if you draw the population, you see the difference is subtle, but again, you see there is a slight difference in the two distribution. The Sub-Alfvénic population here has a slightly higher PVI in the high PVI regions than the Sub-Alfvénic population, right? So we interpret that intermittency is slightly reduced in the Sub-Alfvénic wind. So inside the Alfvén surface, you have slightly less intermittency, right? So that means you have stronger current sheet outside the Alfvén surface. And again, this is, I think, consistent with the picture that we have been discussing in the previous example. Turbulence is enhanced, anisotropy is decreased outside the Alfvén surface, and you have stronger current sheets from the nonlinear evolution. Okay, so we talked about turbulence, we talked about anisotropy, and we talked about intermittency. One final thing is switchbacks, which have been quite a hot topic in Parker observations. And again, without assuming that people know about switchback, I'm going to give a little bit introduction. So here is a typical magnetic field observations from Parker data. Here is about 10 days of data, and here is a zoom in version of the same thing. In both, you see there is the envelope of the magnetic field radial component, right? It stays negative here, but every once in a while, it makes this sudden polarity reversals. So let's look at the zoomed in version here. It has a value, the BR, the radial magnetic field, has a value of about minus 80 nanotesla here, but every once in a while, it makes these jumps. So the magnetic polarity changes from negative and actually goes above 0. So almost changes to positive. So think about it. This is the radial component of the magnetic field. So it's negative, it flips direction almost, the magnetic field, right? And these are called switchbacks. They were observed before Parker at greater heliocentric distance, but they are a prominent feature in the Parker observations. So polarity reversal in the magnetic field directions. Looking at one particular switchback, like I'm showing here. So the magnetic field radial component changes here from positive to negative actually, whereas the magnetic field magnitude, and you can notice that from this figure as well, does not change. So that's a difference between switchbacks and current sheets. Current sheets also have this change of polarity of magnetic field, but in current sheet, your magnetic field magnitude drops to 0. In switchback, the magnetic field magnitude stays constant. Only your polarity reverses. And it is accompanied by a jump in the velocity. So here you see the velocity was about 350 kilometers per second, but at switchback, it jumped to about 600 kilometers per second. So these are known as switchback. Here's a representation from NASA, what the switchbacks may look like in a 3D view. So here's the sun, it's emitting the magnetic field, and the magnetic field lines have this Z or S-shaped kinks, right? And that's what the spacecraft is traversing through and seeing as a switchback. What causes the switchback? Whether they bring some information down from the lower corona, or whether they are being generated due to in situ processes is not clear yet. There are 4 or 5 main lines of theory which try to explain the switchbacks. I'm not going to go into the detail, but just want to mention that it's not settled yet which one of them is clear. But some of these theories make some prediction about switchback inside the Alfvén surface and outside the Alfvén surface. So we thought that these observations can provide some clues, and I'm going to talk about that. So switchbacks, how do you quantify switchback? Usually we do this using this Z parameter. So you calculate this 1 minus cos alpha over 2, where cos alpha is the angle between your instantaneous magnetic field and your background magnetic field, right? Your background magnetic field is given by the average of magnetic field vector, and then you dot product it with the instantaneous magnetic field, and then you calculate the angle. If there is a switchback, this, so which means if the magnetic field polarity actually reverses, this Z parameter will have a value greater than 0.5, right? So for example, I'm showing a figure here. Here you have a switchback, the magnetic field polarity changes, and the Z value jumps more than 0.5, right? Some people nowadays are also calling these small increase in the Z values also switchback. So even though it's not a complete switchback, you don't have this crossing 0.5. Some people are also considering this as a sort of incomplete or a small switchback because it has an enhanced value compared to the mean magnetic field. So here the magnetic field is starting to change polarity, but does not complete its polarity reversal. But this is a proper complete switchback. Anyway, so just like the previous analysis, we calculate the Z values for the sub and super-Alfvénic intervals. You take the log and then you plot the two population here. And you clearly again see there's a shift in the two histograms, right? The super-Alfvénic samples have clearly higher, consistently higher Z values than the sub-Alfvénic intervals. So the switchbacks are stronger in the super-Alfvénic interval than the sub-Alfvénic interval. Again, a table, you can quantify it, most probable and the mean values. Remember I said that a Z value of half, a Z value greater than half denotes a actual switchback or a complete switchback. So the super-Alfvénic sample show this tiny distribution where it actually switchbacks. The sub-Alfvénic intervals actually show none. So in the sub-Alfvénic intervals, we have not had any complete switchbacks yet, zero so far. That does not mean that in the future we won't see any, but at least it makes it unlikely or less likely than the super-Alfvénic intervals that we'll see a switchback. And in any case, the distribution is less. So even the switchbacks which we are seeing in the sub-Alfvénic are weaker than the super-Alfvénic. And this is consistent with two of the theories which were given for the origin of switchback. So remember I did not talk about, but I only showed like 4 or 5 broad theories which tried to explain switchback. Among them, these two papers, one by Raphael et al. Using shear driven switchbacks, and the other one due to the interaction of slow and fast wind. These two predicted that once we go below the Alfvén surface, we should rarely see any switchback at all. And so far, I think the picture is consistent with these two models. So I think that is pretty much it. It brings me to my summary. I'll leave it with this picture. So to summarize, Parker solar probe sampled extended periods of sub-Alfvénic solar wind at a distance of about 16 solar radii. It's the first in situ detection of sub-Alfvénic solar wind in the inner heliosphere by Parker solar probe for extended periods. So we have started to, probe the sort of the lower corona, the region of interest. We compared some properties of sub-Alfvénic periods with the neighboring super-Alfvénic periods, and we found that turbulence decreases inside the Alfvén surface, or Alfvén zone, anisotropy increases, intermittency decreases, and you have weaker switchbacks, and no full switchback so far inside the Alfvén surface from the observations. So these may provide some important previews of the process occurring at much lower altitude. And here's the paper which appeared a couple of weeks ago. And here's my email address. Feel free to get in touch. But I'm happy to take questions right now. Thank you.
All right. Thanks, Riddhi, for the excellent talk. All right. So we're open for questions.
Okay, if I can ask one.
Please go ahead.
Okay. So Riddhi, I mean, you have talked about sub-Alfvénicity, all these things. So, I mean, we have seen that also, I mean, in the Sub-Alfvénic region, the solar wind speed is like, you have, I mean, what I saw from your samples, I mean, most of the cases some of like, I mean, I also saw sometimes 450 or something like, yeah. And more, for all the other cases, like let's say 200 to 50. Now, my question is that, is it true that at this length, I mean, at this distance, I mean, what we call like really near sun solar wind, will it be okay to already classify fast solar wind and slow solar wind, or we have to wait? You think that it is too early to classify them? Is the question already meaningful?
Yeah, so what people are saying that you can just say that anything above 400 is fast solar wind and anything below 400 is slow solar wind, but they are not like the fast and slow solar wind that we see at 1 AU. So at 1 AU, your fast solar winds are always Alfvénic and the slow solar winds are sort of less Alfvénic, right?
Right.
Your cross helicity is less in slow solar wind and so on. In Parker observations, even the slow samples, so for example, here where you have 250 or about 200 kilometers per second, even these, if you calculate the alphanicity will be quite high. So it's not clear yet whether we should.
I mean, there is no one-to-one mapping, you mean, right?
Not in the usual sense, no.
Not in the usual.
So one picture that people are saying, one thing that might happen is these slow solar wind samples later evolve to become fast solar wind.
Right. That's my question. Exactly. Okay. Yeah. And there is some model for that, or this is still obscure?
Yeah. I think Olga Malandraki and people have some models about that.
Okay. Thank you.
Okay. So let me ask. So the 1.5 that Zank, so maybe it is, Subrati, can you kind of clarify what is your view on Taylor hypothesis? So, okay, so maybe you can first tell your work. Subrati can
No,
so
I just sent you a page. I mean, the screenshot with this. I mean, actually, so to be very honest, like the Taylor hypothesis has two parts actually. First is that the fluctuation should be very small with respect to the mean field. That is the first point. And the sum of the mean field and the fluctuation, which is of course for solar wind is almost the mean field, should be very, very greater than the Alfvén speed. That is the two parts. So now for, let's say if you have some system where mean field is very weak, let's say it's very fluctuating with respect to zero, positive and negative values, then your fluctuations will actually determine the Alfvénicity and the Taylor, I mean, applicability of the Taylor hypothesis. But for solar wind, it is actually, so it is simply that Taylor hypothesis simply thinks that, I mean, when you see the fluctuations are frozen in the solar wind. So it is the relative speed with respect to the, I mean, of the fluctuations with respect to the spacecraft. That's how I understand. I mean, so Riddhi can refine maybe.
I agree, totally. I completely ignore the first part because it is usually true, and even in these cases. But yeah, I just focus that the second part is not valid.
Yes.
So, these observations.
Okay, so thanks, Riddhi, again.